So 5's go in the first box. What about the second box? 15. Okay. I wonder how we got those. Now, can someone explain to me how they got 15? You added the 2 right above it, so that the 10 and the 5 make the 15. Does that work for every number we see so far? Yes. Did anybody find the 15 in another way? Ooh, that's kind of cool. So he's saying if you go 1 plus 4 plus 10, that makes 15. Does that always work? Yeah? So what is the rule for that kind of adding? Start anywhere on the edge and go as long as you'd like. So what about this one? Is 1 plus 3 plus 6 plus 10 equal to 20? It is. So there's different names. I mean, I name these interesting patterns in different ways. Since we're in Canada, I call this the hockey stick identity. If you make a hockey stick, then all the numbers in the shaft of the stick will add up to the number in the blade of the stick. In countries where, if I was teaching this in a country where there was no hockey, and they'd look at me like, what are you talking about? Then I might call this the sock identity, because it kind of looks like a sock, depending on where you're from. So yes, that is another way that you could get that number. And I am going to show you a ton of cool things with this triangle. But to start off with, the easiest way is the first way that we mentioned. You can find the next numbers, so the whole next row, just by adding the 2 above it as you go along. So this is Pascal's triangle. We're going to find out how the patterns of these numbers, which is a simple pattern, just add the 1s above it, start with 1s on the edges, and always add the corners above it, and how this relates to a bunch of different things. First of all, we're going to just look at some cool patterns that are in the triangle. So we already saw the hockey stick identity. We've seen how you add the 2 numbers to get the next numbers. And you see how it's symmetrical on the left side and symmetrical on the right side. So there are some other cool things that come out of here. For one, if you look along this row, right, those are just numbers going up by 1. Well, that's not that exciting, I know. But if you ever wanted to add up all the numbers going up by 1, you just have to keep going down and make the hockey stick. And all the numbers from 1 to 6 equal 21. And 1 to 7 would equal 28. Now, some other things that are cool with this is if you look at other diagonal rows, like this diagonal row, 1, 3, 6, 10, 15, those numbers have a name as well. Has anyone ever heard of those numbers? Well, you've heard of those numbers, but do you know what that sequence of numbers is called? Well, those are called the triangle numbers. Triangle numbers because if you start with 1 dot, then add 2 dots, then add 3 dots, you just keep making bigger and bigger triangles. So sometimes those numbers along that are your triangle numbers. And your triangle numbers are just the sum of the first n consecutive numbers starting at 1. If we look at each row as we go along and add up the numbers, what do we find out? So the first number, I've just got 1. Second one, 1 plus 1 is 2. 1 plus 2 plus 1 is 4. What's the next row equal to? 8. Next one, 16. The 8th row. 128. 128 happens to equal what? It equals 128, but 2 to the power of 7. Do we notice that we have our powers of 2? If we add them up, each row adds up to a power of 2. That's kind of cool. What else is there? Well, if you just think of these as numbers, the first one is 1, the second one is 11, the third one is 121, the next one is 1,331. What's special about those numbers? They look nice. They have ones on the end. Beautiful. Yeah, but I want to know what's special about those numbers. How are they related? How is 14,641 something related to 121? This is 11 squared. What's this? Is it 11 cubed? It is. Fascinating. And that's 11 to the 4. So what do you do with this row with the 10s? Because then you think, okay, so it only works up to there. Well, not really, because if you start working backwards, 1, 5, 0, that's a 10. That moves over here, makes 11. That's a 1, moves over here, 6, 1. See how I added the, sort of carried the 1 over? And if you type that into your calculator, that's 11 to the 5. If we use our very last row, right, which should give us 11 to the power of 7, we will get 1, 7, 1, carry the 2 to make 37, carry the 3 to make 38, carry the 3 to make 24, carry the 2 to make 9. Try that on your calculator. Is that 11 to the power of 7? I'm kind of curious. It is! Isn't that cool? I don't know. So this Pascal's triangle also has powers of 11 in it. And it also has the Fibonacci numbers. Do you know what the Fibonacci numbers are? Does anyone know the first Fibonacci number? No? First Fibonacci number is 1. Second Fibonacci number is 1. Third Fibonacci number is 2. Then 3. Then 5. Then 8. Can someone tell me the next 2 Fibonacci numbers? 13 is the next one. And then 21. How do you find the next Fibonacci number? You add the previous 2. Now the Fibonacci numbers are probably, in math lore, some of the most famous numbers because of all the places that they appear in nature. Here, we'll get off topic just for a bit. So, Fibonacci numbers. First of all, where did they start? They started with a hypothetical situation. Hypothetical situation is you start off with one pair of baby bunnies. So in total, how many pairs of bunnies do you have? You have one pair of baby bunnies. The next season, and I don't know how long the season is for bunnies, but bunnies apparently produce rapidly. So maybe you're a baby bunny for a month and then you're an adult? I'm not sure. It might be that you're a baby bunny for 5 months and then you become an adult. Anyways, one season later, these baby bunnies are no longer baby bunnies. They're adult bunnies. So the next season, you have one pair of adult bunnies. And so your total pairs of bunnies is still 1. Now, in this hypothetical situation that Fibonacci created, so you create a crazy situation, they name numbers after you. It's cool. So you create your own crazy situation. If it becomes important, you'll be a famous number person. If it doesn't, no one will remember you, but that's okay. Okay. What happens the next season? Yeah, and in this hypothetical situation, our pair of adult bunnies always has one pair of baby bunnies. So the next season, these adult bunnies are still adults, but now you have a new set of baby bunnies. And so you have a total of 2 pairs of rabbits. The next season, these babies become adults. So now you have 2 pairs of adult bunnies, but only one of these were adults last season. So they have another set of bunnies. And now we have 3 pairs of bunnies. The next season, these become adults. These 2 had babies. Whew. And we're not worried about any bunny incest or anything like that. Okay? And these are hypothetical bunnies in an ideal situation that never die. And so what ends up happening is these bunnies increase, and the next one will be 8, and the next one will be 13, and so on, and so on, and so on. And these numbers seem like they shouldn't be that important, but then people started noticing that there are places all over in nature where these numbers appear. Most flowers have flower petals that are in 5s, 8s, 13s, 21s. Why do flowers not have petals in between? Why do they seem to grow in that way? And if you look at the sunflower, a sunflower has a bunch of seeds, and if you look at the seeds, you can see a spiral in one direction. At the same time, here I'll use a different color. If you look in another direction, you see another spiral, just how they grow. And if you count the number of seeds along the edge of one spiral, you get 1 Fibonacci. And if you count the edge according to the other spiral, you get the next Fibonacci number. So that's kind of weird and just kind of a coincidence. But then you look at how plants grow. And when a plant grows, it comes out of the ground. And it's just a little stem. And it's weak, like a baby stem. And the next series of growth, what happens? That stem grows stronger. And once it's strong, well, then the next set, it branches off into a weak one, and the strong one continues. And the next series, the strong one branches off again, and the weak one becomes strong. Whoops, that's supposed to be green. And so if you look at cross sections, you started with 1, 1, and then 2, and then 3. And if you keep this going, it models how a plant grows. And then probably one of the most famous places where the Fibonacci numbers come up is, like as far as in math, you see on textbooks, tons of times on the front of a math textbook, they have a picture of a snail. And you go, why do they have a picture of a snail? Well, the curve of a snail follows the Fibonacci numbers. So if you start with a square, that's 1 by 1, and then draw another square, that's 1 by 1. And then off the edge, you could draw a square that was 2 by 2, and off this edge, draw a square that's 3 by 3, and then a square that's 5 by 5. And if you start in the corners and draw a curve through the corners, that is the shape of a snail and how a snail grows. So it gets a little crazy. And as we get bigger and bigger and bigger and bigger Fibonacci numbers, and we divide them over and over and over again. So you start with 8 divided by 5, you get 1.6. Then you do 13 divided by 8, and you get 1.625. Then you do 21 over 13, and you get 1.6 something. 1.615. And the number is going back and forth, and it's getting closer to a number, and the number that it gets closer to is, I think that, let's try what that equals to. 1 plus the square root of 5 divided by 2, 1.618. Which is called the golden ratio. And this golden ratio is a crazy thing because it shows up all over in nature. Okay? And it's sometimes called the golden ratio, sometimes called the golden proportion. Have you ever heard, someone walking by and they say, oh, that person looks a little disproportionate because their arms are like dragging on the ground, or, something, their legs are way too long. So we have a sense of what a proper proportion is and what's not a proper proportion. And it apparently is really related to this number. Because if you would measure, for example, how tall you are and divide by how high it is up to your belly button, it'll come out really close to 1.618. If you measure and it's like weird, like if your belly button is halfway your height, right? All of a sudden the person goes, wow, that person has short legs and a really tall body. And that happens. But you would go, that's a little disproportionate. We're all a little bit disproportionate. There's very few of us that are the perfect golden ratio. But there's all sorts of parts of our body. Like if you divide the space between this knuckle, and then this one and this one, they all make that golden ratio. So it's a really cool thing that appears all sorts of places in nature, and then we see it start to appear in art and music. And it's really interesting that, for example, I'll try my best. I'm not sure. Oh, that looks like a nice rectangle. And it's called the golden rectangle, if I've drawn it correctly. Now, the golden rectangle happens to be that if you divide this side by this side, that you get the golden ratio. And if you have the golden rectangle, it seems like a lot of things in life and a lot of things that are designed start getting designed at that shape. They found that people will buy apple juice if it's in that carton shape rather than if it's in a square. They say, oh, this just looks nicer, right? They make your credit card in a golden ratio. Say, oh, this is nice. I should spend money. Yeah. And the Parthenon in Greece, the famous Greek structure, when it was designed, its ratio has the golden rectangle in it. Did they know that when they designed it, or when they were just trying to draw, the architects said, what will be the most beautiful building to look at? Did they just draw that, and it just happens to be that the golden rectangle appears in that? And then you've got stuff like music. Like, I think, is it Beethoven's fifth, or is this ninth? The one that goes, bum, 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 bum. Which one is that one? The fifth. Bum, 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 bum. Have you heard that one before? Bum, 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 bum. And what, now, I don't know if I have my Fibonacci numbers right. So what is it? It goes 21, then 34, then I'll go 55, and then 89, and then 133, and then 200 and... Is that right? Did I make any mistakes along the way? Oh, this is 134. There we go. And this would be 200. This would be 3 then. 223. And then 335. So what Beethoven did in his Fifth Symphony is music is separated into measures. 350. Yeah, okay. So we might have made adding mistakes along the way. It doesn't matter. But what Beethoven did is that along the way, he was introducing his theme, and then he took approximately, I'm not sure if it's these two numbers or these two numbers, but took 357 measures of playing around with that theme. And went all over with that. And then at the beginning, after doing that for 357 measures, he reintroduces the theme a second time and then takes 223 measures to finish his piece. Because that spacing of a golden ratio felt that it was the most beautiful to the ear to hear it in that kind of section. You're able to listen to variations for a certain amount of time, and then when it's introduced again, a little bit of shorter time is nicer before that song finishes. And so we start to see, did he know about these numbers? Did he do that on purpose because of mathematicians at the day, or did he just think that that sounded the best? I don't know. But some very cool things. Anyways, we digressed from Pascal's triangle. Fibonacci numbers are pretty fascinating. So where do the Fibonacci numbers appear in Pascal's triangle? Well, if you take, yeah, that looks nice. If you take that line, and we're going to clone that line, and just drag it down until it hits the next number, it's a 1. And drag it down until it's, the next number, it hits a 1 and a 1. 1 plus 1 is 2, and then it hits a 1 and 2. 1 plus 2 is 3. And then 1 plus 3 plus 1 is 5. And if you keep dragging it on that angle, you will hit all of the Fibonacci numbers. So these are all fascinating things that come with Pascal's triangle. There's other things. If you would go to Pascal's triangle, here, if you would go to Pascal's triangle and decide to color in all of the even numbers, and kept going over and over and over again, and made Pascal's triangle really large, what would you get? You would get, let's go, here, I've got to find it this way, it's faster. You'd get Sierpinski's triangle. Anybody ever heard of Sierpinski's triangle? Oh, we're getting off topic today. Is that okay? All right. There, let's look at Sierpinski's triangle. Let's look at the fast version. No, I don't know if I want the fast version. Do I have final 1? That one looks like it would be a good one. There. We got the fast version, slow version. Pick a color. Purple? Do I have purple on there? Magic. Oh. Yeah, I asked a student once to create this. Now, Sierpinski's triangle is something called a fractal, where you zoom in and you always see the same thing over and over and over again. The way that this one is designed is by pure randomness. Somewhat pure randomness. You name each corner 1, 2, 3. You roll a dice. If you get a 1 or a 2, you've chosen the top left corner, 3 or 4 top right corner, 5 or 6 bottom corner. You randomly start anywhere on here with a dot. So it looks like, I'm guessing that this was the very first dot right there, this green one, down there. And the very first iteration, they decided to roll a 1 or 2. Because what happens is every time you roll, you start where the dot you're at, and you draw a dot halfway towards that. So there's another dot right here, so which makes me think that that's where they started. And then you do that again. And this probably did this millions and millions and millions of times. Once you get in the triangle, you can't get out. That's how I know that these points that are on the outside were probably the starting points. And no matter where you randomly start, and no matter what random order you choose things in, it creates Sierpinski's triangle. And so some people believe that these kind of random generated objects that always make the same object every time, even though everything's random every single time, might be a little bit of an explanation of how DNA works. Like, how is it that it's like you have a seed and it always produces somewhat the same plant, but not the same plant? You know, people all look somewhat the same, but not quite the same. But it's not like we get some weird variations where, you know, someone comes out with 6 arms. Like, well, how did that happen? Right? We don't have those variations. We might have variations on how many hairs are on our top of our head, but maybe we all start off with the same. I'm not sure. is that, and then just how it grows or whatnot. So anyways, another fascinating thing that comes out of Pascal's triangle. But where are we going with this? What do we want to see out of Pascal's triangle? How is this related to Mississippi and how many subs there are at Subway? Well, if you had worked forward onto the next page and you looked at combinations, if you evaluated 4 choose 0, 4 choose 1, 4 choose 2, 4 choose 3, 4 choose 4, you start to see that, hey, that's the same as one of my rows in Pascal's triangle. And maybe you remember seeing Pascal's triangle. You probably don't remember seeing it, but remember when John was trying to get to the library? I don't know if it was John or whoever it was, right? And there was one way to go to each of these and one way to go to each of these, and then Pascal's triangle started showing up on his way to the library for the number of pathways as he went along. And so now we can rewrite Pascal's triangle with combinations. So we can have 2 choose 0, 2 choose 1, or we can just cheat and slide them all in there. And so on and so forth. Pretty cool. And this is going to lead us to something called the binomial theorem. Now, I don't know, should we go into the binomial theorem already, or should we leave that for Tuesday? I'll give you a little taste of it now, and then we'll revisit it on Tuesday. So the binomial theorem is all about what would happen if you took two things, x plus y, and squared them. Well, you've done that before, right? What's x plus y times x plus y? X squared plus, well, close, plus, yes, there's going to be a 2 in front there, and then plus y squared. So then you say to yourself, well, what would happen if I wanted to do x plus y cubed? Well, that would be x plus y times x plus y times x plus y, which would be x squared plus 2xy plus y squared times another x plus y. And what do we get? We get x cubed plus only 1x cubed, and then 3x squareds y plus 3xy squareds plus 1 y cubed. Now you guys are good at patterns and noticing things. So if I wanted to do x plus y to the 4, what do you think you'll get? 1x to the 4, okay, plus 4x to the 3y plus 6x squared y squared 4 plus 1 y to the 4. And how does this relate to combinations? Why does this work? Why is the coefficient of x squared y squared 6? And why is the coefficient of xy cubed 4? It is the numbers of the triangle, but why does that work? Why does that happen? Like, why is it when I multiply x plus y times x plus y times x plus y times x plus y, why does it get us that? Well, the idea is the following. When this all multiplies out, and if you would draw all the arrows of all the things that multiply together, what ends up happening is this x will get multiplied by here, and it will get multiplied by there. And then that would get multiplied by this one, and this one, and this would get multiplied. And there'd be like foil would go crazy with the arrows with this one when you try to show everything that's happening. But to make it a little bit more simple, each one of these items that appears is the result of one of each of these things chosen all the way through. So for example, if you want x to the 4, can you see that in this one there is no y's? And so an x to the 4 means that you need to choose no y's. We have 4 y's, and we don't want to choose any of them. How many ways could that be done? One way. But let's look at the x squared, y squared. And you can think of this as either choosing the y's or choosing the x's. But we have 4 y's. In order to make an x squared, y squared, you would need to choose 2 y's and 2 x's. How many ways could that be done? If the order doesn't matter, because choosing this y and this y is the same as choosing this y and this y when you're multiplying. That would have resulted in the same thing. And so this number in front of the x squared, y squared is saying you have 4 y's and you want to choose 2 of them. How many ways could that be done? 6 ways. If you have 4 y's and you need to choose all 4 of them, the only way you get a y to the 4 is when all of those last terms multiply, and that happens only once. But you could get 3 y's and an x by having the 3 y's in this x, the 3 y's in this x, the 3 y's in this x, or the 3 y's in this x. Well, that's the same as 4 choose 3. Now, I chose to say how many ways could you choose y so that it matched with what we wrote in our diagram before, starting with 4 choose 0 and going up to 4 choose 4. And the reason this pattern is helpful is because we are going to look at expanding things that are huge. That if you did them by hand, they take forever. X plus 3y to the 8. Because you'd have x plus 3y, x plus 3y, 8 times. Oh. And then you have to multiply 2 of them and get the answer. Then multiply 2 more and get the answer. And it would take a very long time. But noticing this pattern is going to allow us to solve these quicker. And that's what we're going to look at on Tuesday. So for the remaining of class today, you can work on the questions that are in the Assess the Understanding here, or you can work on that combination sheet that I gave you last class.